Hello everyone, my name is Samuel Wilson and today I will be presenting our work on SAFE, Sensitivity-Aware Features for Out-of-Distribution Object Detection. This is a joint work between the QUT Centre for Robotics and the University of Adelaide's Australian Institute for Machine Learning, with my fellow co-authors Toby Fisher, Faraz Dayub, Dimity Miller and Nico Sunderhav. It is well known that deep neural networks perform well when tested on data that closely matches their training distribution. However, when tested on out-of-distribution samples, deep neural networks are often overconfident in their erroneous predictions. More concretely, neural networks fail silently on out-of-distribution samples. To address this challenge, many methods propose to use multi-scale feature maps extracted from the backbone of a neural network, providing some statistical analysis of these features and then using that statistical analysis to determine if a sample is out of distribution or not. These methods are effective. They are often reliant on the specific layer selection used for a specific type of out of distribution data. As an example, if we were to change the out of distribution data presented to the model, the importance of each individual layer may actually shift towards a different importance for the specific type of out of distribution data being observed. Thus, we ask the question in this paper, can we identify a set of consistently powerful layers for detecting out-of-distribution objects? In order to identify a set of these consistently powerful layers, we look at two core characteristics that are common within neural networks. The first of these is sensitivity, which refers to the ability of the network to preserve distances in the input space in the network's hidden space, or in the features. As a result of this sensitivity, the input differences caused by out-of-distribution samples will appear in the network features, and recent work has shown that residual connections are sufficient to ensure that a network is sensitive to input changes. Secondly, batch normalization layers, a common normalization technique used in deep networks, has recently been shown empirically to trigger abnormal activations when the parameters of the batch normalization do not match the test data, as is the case in out-of-distribution data. From this, we define safe layers as residual connections that are followed immediately by a batch normalization layer. As a result, these safe layers will exhibit the characteristics of both residual connections and batch normalization layers, making them sensitive to out-of-distribution data. These layers are not actually that uncommon, as 4 of them exist within a single ResNet network. In order to leverage our safe layers, we propose a surrogate training methodology using an auxiliary meta-classifier network. To begin with, for each training sample, we generate both its bounding boxes and an adversarial example using FGSM. Pairs, we extract the feature maps from the safe layers of the backbone of the object detector network. These are then subsequently combined with the bounding boxes predicted on the original images through region of interest pooling operations to create object-specific feature vectors for each of the objects within the image. These are used as training samples for the auxiliary meta-classifier network to determine if an object is perturbed or unperturbed. During testing, we repeat the same process of safe layer feature extraction combined with region of interest pooling using the auxiliary MLP to detect if a sample is out of distribution or not. Our results show that SAFE significantly improves upon the state-of-the-art in out of distribution object detection. More specifically, SAFE more than halves the false positive rate of previous state-of-the-art without requiring retraining of the base network like many state-of-the-art methods do. Additionally, we observe that the safe layers are in fact among the most consistently powerful layers in the network across distributional shifts, as we can see with these blue layers here. Furthermore, the safe layers, which are only 4 layers within the network, outperform layer subsets which contain significantly more layers and hence more information. Thank you for listening. If you're interested in learning more, please come find me at the Vision Applications and Systems poster session on Friday the 6th between 2:30 and 4:30 p.m. Thank you.